Good morning, everyone. I'm Qazi Saakat Islam, and I'm in my first year pursuing BSc Honors in Physics. Today, I'm going to present a self-directed project of mine, and this project is about formulation of the problem of finding volume of n sphere and obtaining an answer. So, in order to subject the above idea to analysis, one must first obtain a precise analytical definition of n sphere. So, let us first begin by defining what an n sphere or sphere in high dimension means. So, if you look at the two special cases which are available to us, the defining property of sphere in 2 dimension and in 3 dimension is that it is basically the locus of all points that are the same distance from another point, which we generally call the center. So we know that in 2 dimension, the distance is given by square root of x squared plus y squared and square root of x squared plus y squared plus z squared in 3 dimensions. So if we equate them to a constant, we can define sphere in the respective dimensions. So now it is evident that we need to generalize a notion of distance in order to define a sphere in n dimensions. It is evident that if we had 2 points given by x1, x2, x3 till xn and y1, y2 to yn, then we can define a notion of distance dx comma y as shown in figure 1.3. Now, however, naturally, a question arises, which is that is this definition a valid notion of distance? We see that this already takes into account the special cases we discussed for 2 dimensions and 3 dimensions. However, if we want to answer the question more rigorously, what we have to do is we have to show that this distance measure satisfies the axioms of distance measure as shown in figure 1.4. This includes some basic properties we would like our distance measure to respect. For example, the fact that distance has to between 2 points has to always be greater than 0. Then the fact that distance between 2 points is 0 if and only if both are the same and identical points. Sufficient it is to say that this does respect all of the axioms. So we can use this as a valid notion of distance. So if you just equate it to a constant and square it, we can obtain a definition for n sphere as shown in figure 1.5. So now having already defined what an n sphere is, let us now establish the problem statement. So now in order to find the volume of an n sphere, we have to basically integrate over the region R, which is defined by the equation of n sphere. And this is a multiple integral that we have to evaluate. So now the difficulty in the evaluation of the problem generally arises from the fact that the limits are very difficult to determine. In 2 dimensions and 3 dimensions, this difficulty is overcome by using polar coordinates and spherical coordinates. So this naturally motivates us to find the generalization of spherical coordinate transformation that could exploit the symmetry of our problem and make it easier to evaluate the integral. So thus we arrive at the subproblem of generalizing the spherical coordinates. So let us actually consider the n equals to 2 and n equals to 3 case and construct the spherical coordinates to gain an insight about how to generalize for to n dimensions. So on the left in figure 3.1, we have the n equals to 2 case, and we generally first begin by defining an angle θ1 with respect to the x1 axis, and we proceed by resolving the vector into its components, and we arrive at the results we want. Just note that θ1 ranges from 0 to 2 pi here, while r ranges from 0 to infinity. In the n equals to 3 case on the right, what we do is we first begin by defining an angle θ1 with respect to the x1 axis. Then first we consider its projection on the x1 axis, and then we consider its projection on the x2, x3 plane. Then we proceed exactly how we did for n equals to 2 case by defining an angle θ2 with respect to the x2 axis. Now, the question that I'm interested in asking is, can we actually do the 3-dimensional case without actually employing 3-dimensional visualization? Answering this will lead us to be able to proceed with construction of spherical coordinates in higher dimensions. So let us look at how we can think. This is just a heuristical way of uh, doing the same thing that we saw previously. But I shall justify later on why whatever coordinate transformations I obtain from this heuristical method is justified. So what we do is we first construct x1 and then we consider x2, x3 conjointly as one plane. Then we simply resolve after defining the angle theta1 with respect to x1 axis, we simply resolve how we resolve. And on the x2, x3 plane, we see we have the resolved component as r sine theta1, which becomes the new radius for uh, consideration when we split the x2, x3 axis into individual x2 and x3 axis. And then again, after defining the angle theta2, we resolve them into components. Now, this method of thinking actually seamlessly generalizes, and you can see the same I've done for 4 dimension. So first I've considered x1 and the axis x2, x3, x4 conjointly. Then I've split that into x2 and x3, x4 conjointly. Then the last again recursively. So when you do this, you obtain a few results, which I shall show here. And from here, we can directly go to the generalized spherical coordinates. So what we have arrived is at our general spherical coordinates through mathematical induction from the patterns that we saw previously. Note that theta1 ranges from 0 to infinity, and theta2, theta3, all the way till theta n minus 1 ranges from 0 to pi, and theta n ranges from 0 to 2 pi. So how do we know that this is a valid generalization? Well, actually, to know that this is valid, to show that this satisfies the definition of n sphere that we came up with. And in fact, you can check it does indeed satisfy the definition. So we can proceed without any further complications. So now the evaluation of integral, we have to actually change the variables from x, which are Cartesian coordinates, to theta, generalized spherical coordinates. So a crucial notion when changing changing variables in multiple integral is the Jacobian. So let us actually examine it. So basically, whenever you're considering a transformation T from a coordinate system, say UV to XY, the areas and volumes get scaled up by an amount which is given by the Jacobian. So when you're changing, say, variables from Cartesian to spherical coordinates, then you have to multiply by this Jacobian factor as shown in the diagram here, so that to preserve the equality of the integrals before and after the transformation, you have to multiply the Jacobian factor here. So how do we actually compute the Jacobian? So as you can see in figure 4.3, the determinant of this matrix will give you the Jacobian, and the ith and jth, the element in the ith row jth column is given by taking the partial derivative of xi with respect to theta j, where xi is nothing but the spherical coordinate transformation that we have already discussed. Now, computation of this becomes quite tedious when you try to compute them out by hand. So I have used an algorithm to compute them out for me, and here are the results I have obtained. So the Jacobians till n equals to 6 dimensions are shown here, and from that you can easily conjecture a form which is shown in figure 5.6 to be the Jacobian for n dimensions. Having dealt with the Jacobian, let us come to the crux of the problem, which is to finally figure out the volume integration. So under the change of variables from Cartesian to spherical coordinates, we see that the problem statement then simplifies to the following after changing and accounting for the Jacobian. And we have to just put the limits in from 0 to r, 0 to pi, because I've already discussed the ranges from which theta1, theta2, and so on range from. So when you plug in those limits and you just do the following steps and simplify the integration, then you obtain the following form. So note that because out here theta2, theta3, and so on and so forth are just variables inside dummy variables inside definite integration. So we can swap them out for phi and it won't change the answer. So the way we evaluate this form that we have obtained for the volume is by using the reduction of power identity that you're probably aware of. And then if you just consider the integral of 0 to pi of sine to the power of n x dx to be in, then we can use the recursive relationship as shown in 5.3 to obtain the values. So here are a few volumes that I have computed out, and these results match the ones that were obtained in literature as well. So actually, now is the final. Let me come to the conclusion of and discuss some of the results. So here I've plotted the dimension n versus the volume of the n sphere. So from the graph itself, we can already see a few counterintuitive results. We see that, for example, the blue curve, which is a unit n sphere, you see there's a maximum which happens at around, I guess, n equals to 5. So basically, as you keep increasing the dimensions, when you reach n equals to 5, that's the point where you have the maximum volume, after which the volume starts to decrease. And what's also interesting is the fact that as you keep increasing n, as you tend n to infinity, the volume tends towards 0. So it is as if the higher you go in dimensions, the space that you have is shrinking in a certain sense. Also, because the smooth curve seems to reasonably fit the data that I've obtained here, you can reasonably answer the question of what is the volume of a sphere with dimensions, say square root of 2, or say what is the dimension of a sphere with dimension n equals 2.5. What is the volume of a sphere with dimension n equals 2.5, and so on. Also, what we see is that the peak value, which I was discussing, seems to shift as you increase the radius values. So these are the final results I have obtained. And so thank you for listening to me. And there were a lot of issues that I didn't go in detail with because of the time constraint. So if you're interested, you can get in touch with me. You can email me, or you can WhatsApp me on my contact number here. Thank you.
Thank you, Kazi. Thank you for your introduction and presentation to this particular problem. If there is any question, now it is open for questions or comments. Yes. Bimal sir, please ask your question. Kazi, can you hear me?
Yeah. Yes, sir, I can hear you. I think sir is muted.
Sir,
I can
please
see
unmute,
sir.
Yes, Kaji,
yes,
your
sir.
work really appreciable, really very nice.
Thank you very much, sir.
You have thought something. Some question you have shown that when we are going from very low dimension to very high dimension,
yes,
the space consumed is less.
Yes.
Right.
Yes. Yes.
Have you any kind of thought or in this process why it is going
yeah
so?
Okay, I can give you a sense. I anticipated that I would have this question, so I can give you a sense of why analytical sense of why the volume should kind of decrease. The fact is that when you look at the equation of a sphere, let's say in 3 dimensions, it's x squared plus y squared plus z squared is equals to a constant, radius squared basically. So when you choose, let's say x equals to 0.5, the choices of y and z are constrained in such a way that it has to equal 1 at the end. So, but if I added another variable, let's say y squared plus z squared plus w squared, now that whatever was the remaining has to be distributed amongst these 3 variables. So they become less in turn. So what happens is, in a certain sense, as you go higher in dimensions, what happens is the points become closer in a certain way, which is why I suppose the space is getting constricted. Does that answer your question? Was I able to provide a reasonable?
Hey, yes, actually, let's say your explanation something just you are thinking something. So okay, we'll talk later also.
Yes, sir.
Try to
Yeah.
find.
Yes.
Yes. Okay.